Okay, today we're going to continue with our trig identities, and we're going to look at some different ones. So in our first lesson we had the reciprocals. The secant is 1 over cos, and we did the sine squared plus cos squared equals 1, the Pythagorean theorem ones. Today what we're going to look at is sum and difference and double identities. So they work pretty much the same. The only thing that we want to be careful of is today we're not going to do so much of the proving. We'll save that for the next lesson. But we're going to quite often use sum and different ones to simplify or to rearrange an equation. And then also we're going to use them to help us find exact values instead of just relying on our calculator to get decimals. So we'll start with our basic sum identities. So the first one is sine A plus B equals sine A cos B plus cos A sine B. So what that means is we can take a question, and if we have two different angles, we can break it apart. So for example, if we look at sine 12 plus 23. So obviously on your calculator we could just type in sine of 35 degrees, hit equals, and that gives us 0.7574. But what we want to do is, could we write this a different way? So the first identity is take the sine of the first, so sine 12, cos of the second, cos 23, then we add cos 12 and sine 23. So if we actually do those on our calculators, we see that our answers are indeed the same. So what that means is, quite often what we're going to do is actually solve these as exact values. And sometimes we'll work backwards. So if I say solve sine 75 as an exact value, we don't have 75 as being one of our perfect triangles. Remember, it was 30s, 45s, or 60s. But what we do know is 75 can actually be broken apart into 45 and 30. So if we take this new formula and use the identity, so that'd be the same thing as sine 45 cos 30 plus cos 45 sine 30, then we can use our exact values and go from there. So sine of 45 is 1 over root 2, cos 30 is root 3 over 2, cos 45 1 over root 2 again, sine 30 1/2. But because we're multiplying these, it kind of gets a little bit ugly. So remember, we can actually change 1 over root 2 into root 2 over 2, which is just by rationalizing the denominator. So if we use the other form, so we get root 2 over 2 times root 3 over 2, which will simplify to root 6 over 2, and then root 2 over 2 times 1/2, that would be root 2 over 2, and then we can actually put those together, so root 6 plus root 2 all over 2, and then we just leave our answer like that. Okay, if we wanted to leave it as 1 over root 2, you could have done that. So let's just kind of go from this step. We'd have root 3 over 2 root 2, if we multiply those, and then on the top we'd have 1 over 2 root 2, so we could just write this as root 3 plus 1 over 2 root 2. So that answer, or the root 6 plus root 2, both identical solutions. So that works for sines, but it also works for cosine. So cos A plus B looks a little differently. Instead of it being both of them, it's cos. So cos 60 plus cos 45 for this example. And then we subtract sine 60 sine 45. And once again, we can use exact values, and we would do pretty much get the exact same thing. So cos 60 is 1/2, 45 root 2 over 2 if we do the alternate form, sine 60 root 3 over 2, sine 45 root 2 over 2, and we just simplify much like we did in the previous example. The tangent one is a little bit different, and we actually don't use this one all that much, but it does work as well. So if we have tan of two angles, it's tan plus tan on the top minus 1 times tan on the bottom. So if we look at this example, we've got tan 40 plus 25, and let's just approximate it again. So if we put in tan 65, we get 2.14. So let's try the identity. We go tan 40 plus tan 25 on the top. We should probably put that in brackets. Divided by 1 minus tan 40, tan 25 on the bottom. Do the decimals, and we do indeed get the same thing. So the sum identities and difference identities are almost identical, just one's a plus, one's a minus. So if we remember back in the first one, we had sine A plus B. It was sine cos plus cosine. And then when we had cos A plus B, it was cos minus sine. So you can see they just sort of work the opposite, and the tan also works the same. If we had tan A plus B in the original, it was plus on the top and minus on the bottom. So the difference identities are exactly the same thing, just your signs change. So be careful. All of these are on your formula sheet, so you can always check that to make sure you get the correct positive or negative. So let's go through an example. So this one says, write the expression as a single function. So we can see we've got cos plus sine sine. So if we go back to our question, cos cos plus sine sine, that's going to be this one. So that'll be cos A minus B. So what that means is we can write this as cos 32 minus 50. We could simplify that to be cosine of negative 18 degrees. And that's it. So that would be our single function. And if we needed to solve it, we could from there. Let's look at the next one. We got 2 tan over 1 minus tan squared. So let's go back to the identity. So you can see we actually have, looks kind of weird. We've got 2 tan on the top. So 2 tan pi by 6 and then 1 minus tan squared. So it's kind of weird if we go back to our tan plus. So we have tan A plus B, we got tan A plus B on the top. So that's the one we want to use, but what's weird about this case is both angles are the same. So we actually have tan of A plus A. They're both the exact same angle. So let's simplify that. That would give us tan of pi by 6 plus pi by 6. Right? So if we have that, it was 2, our tan pi by 6 plus pi by 6. That gave us the tan plus tan on the top, which is 2 tan, and then 1 minus tan squared, which is exactly what the question is. It is, so that's it. So we have tan of plus pi by 6 plus pi by 6. So we could simplify that to 2 pi by 6, or we could even simplify that further to pi by 3. So tan of pi by 3 is indeed the exact same as all this, which is a lot easier. So these identities work pretty good, and this last one that we looked at, because both angles were the same, is sort of a special case. So when we have special cases where they're both the exact same angle, we actually have a couple other identities we can use. So if we had sine 30 and 30, we can write that as sine of 2 times 30, right? Or if I gave you sine 60, we could break that apart into sine of 2 times 30. And then once we have that, we've got these new identities to work with. So the new one is sine of 2 times an angle is the exact same thing as 2 times sine times cos. So sine of 30 times 30 would be the same thing as sine of 2 times 30. So that's going to be the same as 2 sine 30 cos 30. And then once again, we can use exact values. So 2 times a half times root 3 over 2, which would simplify to just root 3 over 2. And if we go from our original, right, sine 230 is the same thing as sine 60, which we know is root 3 over 2. So this identity does indeed work. So that's our sine one. That's our main one for sine. The cosine one is a little bit different. It looks sort of like a Pythagorean theorem one. So if I gave you cosine of 2 times pi by 4, so if we had 2 pi by 4s, we could write that as cosine pi by 4 squared minus sine pi by 4 squared. So the cosine, because they sort of use a Pythagorean, we can actually simplify this a little bit too. We could rearrange them into one of the other forms just using a combination of the two theorems. This one that we have here at the top, plus our a squared plus b squared equals c squared theorem that we used in the previous lesson. Put the two together, we could get any of the other two forms. And then the last one, the tan one, you can see is exactly the same as our last answer. So our previous example we had here was 2 tan pi over 1 minus tan squared. So we can see that's actually our double identity for tan. So these double identities are just kind of simplified versions of the sum and difference ones. Okay, so let's go through a couple different examples. We got sine 2x. So if we go back to our identities, sine 2 is 2 sine cos. So let's change that. So we have 2 times sine x cos x on top. And our bottom one, cos 2x minus 1. So you can see we got cos 2x. And let's use this bottom one. If we bring the 1 over, that would give us cos 2x minus 1. And that's going to equal to minus 2 sine squared. So that's what we're going to use on the bottom, minus 2 sine squared. Okay, so we're just kind of putting the two identities together. Now from here we can see we've got a sine on the top we can cancel. We have a sine squared on the bottom, so we can cancel one of those, but not both of them, just the one. And then we also have a 2 that we can cancel. So that'd be the same thing as just cos x on top and minus sine right? Not the 2 canceled. So just minus sine x on the bottom. And we also know that cos over sine is the same thing as a cotan. So we could write that as just negative cotan, and that would be the exact same thing as well. And that's all for today.